Welcome to everyone. My name is Stefano Utili. I am a professor of geotechnical engineering at the School of Engineering, Newcastle University in the UK. Typically, I say I'm afraid because there's also another Newcastle, which is in Australia, the very sunny one. But instead, in the United Kingdom, Newcastle is on the East Coast, so it's quite wet. Anyway, and I'm also the CEO of Optimal Slope, which is the name of a software company that produces a software that in a way I'm going to talk you through. But let's say the presentation is not about, it's really about a concept, if we wish, which is how we can design slopes, optimal slopes. So here in the title, I have like maximum steepness, because the point would be to maximize the steepness of the slope for the same level of safety. So without any further ado, I will start, and maybe I just take this little icon away. Let's see if this can. Okay, so basically, I like to start with the why, with why to bother. Yeah. There was any question there? Or? No. So basically, it's why it's important to optimize the design of pitot profile. And there is a little example that I give, which is Whittle basically is a pit optimizer. It's what is called strategic mine planning. And there is a tutorial where if you just change 1 degree steepness, you get an extra 10 million. So you can imagine, you can associate in your mind the fact that 1 degree of steepness is 10 million for a small mid sort of mine, and can be in excess of 100 million for larger mine. So the key point is, how can we achieve a steeper pit wall? Because clearly we can see immediately the economic benefit without compromising safety, because the whole point is to maintain safety. And the key assumption is the key sort of idea is to abandon the assumption of planar profiles. And here is hopefully a good visual representation of what I'm trying to convey. So here we have a mine. In a simple stratigraphy, it's like a uniform layer, and this mine has been what you can see here is a shell of the mine, calculated according to Whittle, Whittle, which is a strategic mine planning tool. And we can see that the factor of safety of this slope is 1.191, and this factor of safety has been calculated using limit equilibrium method, Rock Science slide 2. And then here instead we have the same mine, so obviously the same material in terms of the stratigraphy, and the only difference is like the shape. So here we can see it's partly concave and partly convex, but let's say this shape is an optimal shape, and I'm going then to define what this optimal means. But the whole point here is just to show you that actually, because of this shape, here we can see the factor of safety is the same, because this factor of safety again has been calculated by limit equilibrium method, looking for the most critical surface. But actually the overall slope angle, so the overall slope angle means the inclination that you get connecting the toe of the slope to the crest, toe to crest, is a 38.6 rather than 34.6. So for the same factor of safety, so without compromising safety, purely changing the shape of the slope, now we have got an increase in terms of the overall inclination, overall slope angle, 4 degrees. And this is a key in order to design more efficient mines. I would like to sort of a little historical excursion in terms of where the idea comes from. And let's say that already Evert Hook looked at the idea of having slopes, non-planar slopes. And here is 77, a chapter of the second edition of Rock Slope Engineering, where basically we can see circular slopes. There is a bit of disturbance. I don't know where it comes from, but yeah, I guess maybe if okay, yeah, now it's gone away. So basically here we can see like that in this chart there is a factor of safety of 1 for straight slope, and instead when slope are like circular concave, the factor of safety increases. So here Hook shows that already in 77, if you have like a non-planar slope, you can get a higher factor of safety. But equally, you can get a lower factor of safety if you get the wrong shape, because here you can see in case of a wholly convex slope, you get a factor of safety which is lower than 1. No? So here we are comparing basically slopes, different slope shape, where the overall inclination is the same. No? The overall inclination is the same, and we change the shape. So clearly we can expect that if you change the shape, but having the same overall inclination, what changes is a factor of safety. And this chart simply tells us that there are some shapes better than others, and the planar shape has no particular reason to be any good. It's just one of the possible shapes. Then there have been other works, and in particular, I can, let's see, this this was my PhD thesis in 2007, and then other groups of researchers, say in Canada and in Australia. And again, these guys, what they did, including myself, was looking at different shapes, and they came to the same conclusion that some shapes are better than the planar shape in terms of the stability of the slope. But the issue in all this work is the fact that people tend to consider uniform slopes, and of course we know that mines in real stratigraphy is never uniform. Now we have different rock layers, and what we wanted to find the best possible shape for any given stratigraphy. So this is why we embarked on this software called Optimal Slope, because I guess the name says what wants to say is on the tin. So the idea is for the software to find the optimal slope, and now I can give a definition of what is optimal. Optimal slope means the shape that allows to find the highest overall slope angle, the steepest possible profile for an assigned stratigraphy. So clearly, we need to allow for different rock layers, rock properties, target factor of safety. So very importantly, the factor of safety is an input. So for any assigned factor of safety, the software will find the optimal shape. And also bench geometry, because as we know, when we have to design a slope, especially a pit wall, so in the context of open pit mines, the bench design is what comes first. So the bench design in a way is business as usual, and then the bench will simply provide a local constraint that is accounted for in the optimization problem. And ramp geometry, so it's also possible to prescribe position and width of a ramp. Because now what happens is there is a natural way to discretize in space, and is considering the bench height. So bench design, as I said, is business as usual. On the basis of the bench height, we now discretize along the vertical coordinate, the slope. So now we have a set of points whose coordinate, actually the z coordinate is unknown, no? Because, sorry, not z, the x coordinate. So we have to find the x coordinate, the horizontal coordinate for all of these points. And this becomes a mathematical optimization problem where we want to find the x coordinates such that what we maximize is the overslope angle. So this is how the problem is cast. In terms of bench design, the bench design, I just want to quickly say that is business as usual, and bench design means that a bench height will be specified together with the bench face inclination and the minimum beam width, according to several considerations: rockfall prevention, to have a minimum beam width that allows also to do drill and blast. So there are several considerations that come into the design of a bench, also to avoid local instabilities. But at the end of the day, once we have these three measurements, bench height, bench facing angle, and the minimum beam width, because let's remember the beam width can be higher than the minimum. Now we get this angle, here it's called alpha max, no? So the bench design tells us that let's say the inclination at the level of this bench, this inclination cannot be exceeded, no? But clearly we can have an inclination which is lower than that. So now I can tell you a little bit more what the software does, because now the idea is to analyze the stability of thousands of profiles. So let's assume now that you fix the overslope angle, no? You fix the overslope angle, and you want to say, for a given overslope angle, what is the best shape? Because you have fixed the overslope angle, there will be only one shape which is best, and this is a shape that gives rise to the highest factor of safety. And this is found, this shape, using limit analysis upper bound method. In a nutshell, we need to make sure that all the possible failure mechanisms are considered. And this is done for many profiles, no? I mentioned hundreds or thousands of profiles, but clearly the algorithm is clever because these calculations are quite heavy. So you need to have a clever algorithm to be able to quickly find the optimal shape for a given overslope angle. And then the next step is to find the maximum overslope angle. So here there is a bit of an iteration which is done in the software, where there is an initial OSA, initial overslope angle. The profile with the maximum factor of safety is found. Then this factor of safety will be either higher or lower than the target factor of safety. So then a new overslope angle will be attempted, and a new best profile for the new specified overslope angle will be found. So basically, typically after 3 or 4 iterations, the profile after 3 or 4 iterations, typically there will be the factor of safety will be within a certain range in terms of the target factor of safety. Typically, you would specify 1%, no? And then now you have your output, which is a profile whose factor of safety, where the factor of safety is what you have prescribed. And now the key point of this final result is a profile that is as steep as possible. So mathematically, you know that your profile is best because it gives rise to the highest possible overslope angle for the specified target factor of safety. So this is just a graphical representation where you can see the various different profiles, and then I want just to comment on this final result. So now this point corresponds to those, let's say, so this red point, no? They are in the middle, more or less in the middle of your bench. So when the software runs mathematically, it's just we have like a piecewise linear profile. But then here you can see instead with the benches, because clearly all in the context of an open pit mine, you have benches. And now you can see that there are 2 profiles, the planar profile in blue and the in orange, the optimal profile. And the optimal profile is steeper. And in green, you can see the amount of excavation which is saved, because you excavate from the top. So actually in green is a visual representation of the amount of rock that you avoid to excavate. Here is it in 3D, because clearly the point is you want to see a 3D representation. So here we have the same mine. Blue is the design according to planar, the traditional design according to planar pit wall. Instead, in orange is the design of the mine where optimal pit wall have been adopted, and in green is a difference of volume. So you can see now a 3D visualization for this mine of the amount of waste rock that has been saved. In terms of demonstrating the benefit, because at the end of the day, I think this academically is a very interesting concept, the topological optimization of slopes. But at the end of the day, I guess mining engineers want to see what is the practical importance. So what difference could make to mining design? So in order to demonstrate this, we have run 4 different case studies. So each case study is about a different mine, and they've all been published open access. So here you can see basically, sorry, let me move this. Here you can see basically the references. So they're all open access, and you can go and look at each of these paper at your own time. But I just want now to go through one case study, because the methodology we have adopted in order to do this design and calculations is the same. So in this case study, is a case study provided by Kinross Gold, is a mine that is located in North America. And here you can see like the block model. And this case study has been published in the Canadian CEng, Canadian, it's called CEng Journal, Canadian Institution of Mining Journal. So here you have like the rock properties. So in this case, you see for the rock or soil, you have just a code, and this is due to confidentiality reason. So we were able to publish the case study, and in the paper, everything is described in detail, but even myself, I don't know where the mine is or the name of the rock. Is not given, but only a code for reasons of confidentiality, as you can imagine. So in this case, also here you can see the typical economic parameters, so gold price, the processing cost, mining cost, metallurgical recovery, etc. And the factor of safety is 1.2. The factor of safety target for the overall slope angle is 1.2. So what we've done here, we need to, first of all, we have 5 different sectors. So here we can see each sector identified by a different color. No? So for each sector of the mine, there will be one 2D cross-section, which is representative. So for each sector, there will be one cross-section which is representative. And then in this cross-section, we don't want to do design as usual. We want to use optimal slope, the software, in order to find the best possible shape to design the pit wall. And here is what you can see. So for sector 2, you can see in blue the planar profile, the traditional planar profile, and instead in red, the profile stemming out of the software. And the same for sector 3, no? So this is just to show you. So also here, in the middle, you have the planar profile, and on the right is instead the optimal profile. And this factor of safety that you can see here were obtained using rock science slide 2, using the Morgenstern and Price method, and also using FLAC. So FLAC 2D, FLAC slope was employed for this. So let's say I just want to note that you know, here we have like 4 different layers, and therefore in this case the optimal shape that results is quite, I would say, is not intuitive. Instead, in the sector 3, where it is simpler, you can say, okay, it's partly convex, partly concave. But for instance, in sector 2, where there are more layers, a bit concave, then convex. But so this is just to say that the optimal shape really is a result of calculations, cannot just be extrapolated from one mine to another, because it depends on the parameter, on the physical properties, geotechnical properties of the layer and their stratigraphy. This factor of safety, however, they are similar. No, they are 1.2 was a target, and now you can see once again the gain. So in case of the optimal profile, we have 34.1 rather than 32.7 and 38.6 rather than 34.6 in terms of inclination. Here I just want to note that in terms of the design of the benches, or let's say operationally, because clearly the question could be, okay, but operationally, how do I, is something that can be implemented, this optimal profile? And I think the answer is, simply looking at this profile, you can see that in terms of the bench, the face inclination, the minimum berm width is the same as it is in the planar profile. The only difference is that if we want to do an optimal profile, clearly this bench width, the bench width, varies with the depth. And for instance, we can see that here there is like something that could be called a geotechnical berm. Here we have again these two, where these two benches, if you can see my mouse, where they're a bit wider. So the point is that the optimal location of these geotechnical benches, berms, is given by the software. So, but in terms of the practical implementation, I would say that from the point of view of fleet equipment, of the operators that have to excavate the mine, there is no difference, because at the end of the day, a pit wall is made by several benches, and here we have benches, and the only difference is that there are some benches where maybe you have a greater width. That's it. And doing this, then we can have a shape that allows to be steeper for the same amount of safety. Now in terms of, so I'm just trying to get rid of this bar. It's always a bit in the way. Okay, let's put it here. So here you can see basically the increase of steepness for each pit wall profile, and in this case the gain was a good, I would say, a good 52, because the point is at the end of the day to talk in terms of MPV. So there is a decrease of stripping ratio, but then because of this decrease of stripping ratio, we have fundamentally less waste rock. So the amount of ore is similar, but the key point is less waste rock, and therefore this means less costs, better stripping ratio, less cost, and therefore in this case was a 30 million increase in MPV. And in order to be consistent, of course, in terms of the in terms of Witters, here we use data mine. In terms of the strategic planning tool, we just follow the same methodology in both cases, so that the only difference is in one case using planar pit, in the other case using optimal pit tool. But in terms of like how we carried out the strategic mine, the pit optimizer, let's say, that was the same for both cases. So that we can rigorously say that this gain is purely due to the different pit wall. This is another case study. Maybe I can go a bit quicker about this case study, and basically this is a McLaughlin, which is a gold mine located in California, and the beauty here is that there is no NDA. So basically, all the data can be retrieved from MineLib, which is a public repository. This is a website. So all the calculation that we did actually can be replicated by everyone. And when I say all the calculation, I mean both. So the design of the pit wall and the pit optimization. In this case, we use Whittle, Giove Whittle, as a pit optimizer. So in this case, it was maybe just simpler in terms of the geology, because we just have one layer for the slope, and factor of safety 1.3. In this case, we also calculated the reduction in terms of footprint. So basically, just to get rid of this bar so people can see down there. So here we have like that the adoption of optimal slopes allow to save around 19% in terms of the carbon footprint. How did we do this calculation? Basically, we calculate the carbon footprint associated with all the main operation. So drill and blast and haulage, all the main mining and transportation operation. So again, it's all described in the paper, but I think this calculation was rigorous in how we came about this estimate of the amount of carbon footprint which was saved. And equally for the NPV, in this case was 60 million US dollar of NPV increase due to, once again, a massive reduction in terms of the amount of waste rock. And here is a summary of this 4K study that you can find in these journals. They're all, as I said, open access. And so you can see that in terms of profit increase, it goes from 12 to 140 million. And in terms of carbon footprint, again, obviously it varies, no? Because the larger the mine, the more will be how much you save. But this is just to say an average reduction was 600,000 tons per mine. Here I just want to give a quick explanation, which I think is just to give a hint of why a better shape can be trusted, no? In terms of allowing to be steeper. So in a nutshell, here what I'm showing is how much ground contributes to resisting the landslide. So we know that, say, if you have a typically planar profile, so just to keep it simple, of course, you could have faults, you could have joints, but here we want to keep it simple because it's more about the conceptual explanation. When you have a uniform layer, say, of soil or rock, uniform layer, isotropic behavior, the failure mechanism tends to be formed by along a narrow shear band. So here in this curve, you need to think like, okay, here there will be the shear band that typically starts from the toe and then develops all the way throughout. No, so really the question is who resists? Where does the resistance to the slope failure come from? The resistance to slope failure comes from an integral, no? From basically summing up, integrating over all this point. But you can see it's a very narrow region. Interestingly, when you have like an optimal shape, rather than having a narrow region, you have a quite wide region where the ground mobilizes, that's the right word, fully mobilizes its strength. Because here, in terms of the planar slope, all these points that you can see now looking at my mouse, they're not doing much. Yes, there will be some stress, but the strength is not mobilized. They don't contribute to resisting the landslide. Instead, in case of an optimal shape, typically you have several mechanisms, several potential failure mechanisms that tend to happen at the same time. So actually, you have a quite wide region where the ground the strength is fully or almost fully mobilized. So this is just to give an explanation from a physical point of view why a certain shape would allow a significant increase of steepness for the same factor of safety. Okay, so until now I've spoken about isotropic rock, or let's say isotropic ground, but we all know that there are discontinuities. So how do we deal with this? And I would say that let's say there are two main causes of anisotropy. So we know that the behavior of rock is anisotropic, and these are, one, the presence of discontinuities. So you may have different joint sets. Typically, you'll have several joint sets that make the rock mass to be anisotropic to so the strength, in particular, what I have in mind is the strength of the rock mass is anisotropic. And also you could have the intact rock. Just the intact rock in itself may manifest anisotropic strength. So these two means that most rock is anisotropic. So how do we deal with this? Actually, we can account, and here I'm just showing some again recent work that I've done in collaboration with a geotechnical consultancy in the US called Cole and Nicholas. Basically, they have done they've come up with a quite powerful method where this is like an Excel spreadsheet. Okay, so here you put the intact rock strength. The intact rock strength in terms of cohesion and friction angle, but also could be in terms of a linearized, let's say, Hooke-Brown. No, so here you have basically intact rock strength. Then for you will have any number of joint sets. What you need to know are the typical information of the joint sets, nothing more. So deep direction, mean length of the joint, mean spacing, and a probability of occurrence. And then this data, I get this data, and plus you see cross-section azimuth, because clearly depending on how I cut with the plane this a 3D rock mass, I will get a different anisotropic strength. So also clearly the direction of the cross section of the plane that is used to cut the rock mass plays a role in determining what? In determining equivalent anisotropic strength parameter. So now we have a function that tells me, expresses cohesion and friction angle as a function of the direction of loading. And this function is what is needed as input in optimal slope to account for anisotropy. So here I just want to talk you very quickly and almost at the end of my presentation through this case study. So we have like, this is a case study from a mine located in Mexico, and 200-meter high slope. And in this case, so the idea now is that in terms of the software now, whenever we consider a failure mechanism, this is just to give you an example. No? So whenever, how do we account for anisotropy? Basically, we have to discretize a failure mechanism, and we have to give a resistance, a strength that is dependent on the loading direction. So you can see along this different segment, these different pieces, every piece has a different direction. So every piece here along this failure mechanism will be associated to a certain inclination, according to which a different value of cohesion and internal friction angle is specified. Then here I'm showing you just the results. So you can see on the bottom the planar profile, and here on the top the optimal counterpart. What do I mean by counterpart? So basically these profiles exhibit similar factor of safety. So here the target was 1.3. But once again, you can see that the optimal profile is always steeper than the planar profile. And depending, you see on this function, so here you can see in the top, this function is what expresses the anisotropic strength of the rock in terms of a cohesion and friction angle that depends on the loading direction. So in this way, we are accounting fully for the presence of any joint discontinuities and of any intact rock strength anisotropy. So doing that, we can basically work out optimal profile for any given, let's say, type of anisotropic strength. And here, just to note that this in vertical is a tension crack. So here we also have the presence of tension crack that is fully accounted for. So this is just a representation to maybe is even better here, where basically depending on the dip of the bed so depending on the inclination, the dip of the bedding plane we have a different amount of gain. So here is to show the overall slope angle for the optimal profile minus the overall slope angle of the planar profile for the same factor of safety. So this basically is an increase of steepness. So we have an increase which typically is up to 3 degrees, but the amount of increase of steepness depends on the physical features of our rock mass. So it will be different depending on the bedding dip, because if you change the bedding dip, you change the amount of the type of anisotropic strength of the rock mass. Just to finish off in terms of the user interface, so Optimal Slope is a compiled MATLAB application that works on the AWS cloud. And so in a way, the user only has to download on his computer a graphical user interface. And why I want to talk about the graphical user interface, because here I think there is the idea to say how the workflow. So the direction, or to say really the best use that I believe can be done in terms of optimal slope. So let's say you start with a stratigraphy. So typically will be a 3D stratigraphy that comes from a geological model, say from Leapfrog Geo, or from AutoCAD, or Maptec, whatever. So we have a stratigraphy. Now this stratigraphy can be imported into our graphical user interface. Sometimes, the stratigraphy may not have all the geotechnical properties. So then we want also the ability to include geotechnical properties if they're not there. No? And by geotechnical properties, I mean the strength of the rock, the unit weight. Then we have to delineate the sector. So the sector is business as usual, is something which is a manual delineation. And now for each sector, we just specify. So in our graphical user interface, you can just for each sector cut using a vertical plane. So here you would have 5 representative section, but basically for each sector you will have a representative section that you use to design the slope. Then all you have to do is to specify a crest point. So, and this crest point clearly will be given by a preliminary analysis. So you will always have a preliminary analysis where you specify more or less where you expect the crest of your slope, or sometimes could be that there are some constraint in terms of the space, no? So you have not much of a choice. So either way, you will have like a crest point. Then you specify a depth, so how much the overall depth is, and then the software will find for you the optimal shape. Software find the optimal shape. Once this is been found, what you want to do is simply to give this shape as an input to the pit optimizer, to the strategic mine planning. So here is like to show you the full workflow. Fundamentally, we know that the overall inclination you can have is a function of the depth of the slope, okay? So the idea is initially you don't know the overall the depth, no? The depth is a result of pit optimization. So then you could then do a quick iteration where you redesign the slope so that really the slope you get is absolutely optimal for the specified depth. And you could even think of doing designing an optimal slope for each pushback. Because the point is to have a very simple and quick transfer of data between the slope optimizer and basically the pit optimizer. So in this respect, this is, I think, my last slide, just to show you that, for instance, in case of Whittle, what we've done is to have a script, a so-called TCL script, that basically automatically assign the inclination in Whittle. These are called zone, no, slope type. So the idea is we run optimal slope, and then from optimal slope we just have a simple script that automatically assigns to each block of the block model the inclination that come out of optimal slope. So basically, in this way, there is no manual, no need to assign manually. That's my point, to assign manually the inclination in the block model. We run optimal slope, and then we get the input applied straight away to Whittle. And this is something that we've also done with data mining. I mean, can be done with any pit optimizer, because at the end of the day, the pit optimizer, the strategic mine planning tool, what he wants is simply to know some inclination for each block of the block model. And I think with this, I come to the conclusion of my presentation.